The connection of the earthing mesh around the substation to the steel reinforcements of building bases and columns is crucial for ensuring electrical safety. Its primary purpose is to bond all conductive parts together into earth, safely dissipating fault currents into the ground. There are two primary methods for achieving this connection: firstly, thermowelding, and secondly, bimetallic connections. Thermowelding is a process that utilizes a specialized welding machine to directly weld the earthing mesh to the steel reinforcements. This method is favored for its ability to create a permanent and low-resistance bond between the two metals, ensuring optimal conductivity. Bimetallic connections, on the other hand, employ a bimetallic connector to join the earthing mesh to the steel reinforcements. These connectors are composed of two dissimilar metals, such as copper and galvanized steel, bonded together to establish a low-resistance connection. Both thermowelding and bimetallic connections are acceptable methods for connecting the earthing mesh to the steel reinforcements. However, thermowelding is generally preferred because it establishes a more permanent and reliable connection. When considering a specific installation approach, it is important to evaluate its compliance with relevant codes and standards. A common method involves using a secondary galvanized steel bar strip welded to the main steel mesh, reinforcing with the copper earthing mesh then connected to the bar via bimetallic connection. This approach is acceptable provided certain conditions are met. Firstly, the secondary galvanized steel bar strip must be adequately sized to handle potential fault currents. Secondly, the bimetallic connection must be approved for use in earthing systems. Thirdly, the connection must adhere strictly to the manufacturer's instructions. To ensure compliance with all applicable codes and standards, it is recommended to have a qualified earthing engineer review the proposed installation. When dealing with electrical systems, safety is of paramount importance. Proper earthing practices are essential for protecting personnel and equipment from electrical hazards. Understanding the principles of earthing and the various methods available for creating effective connections is crucial for electrical engineers and technicians. In the context of substation earthing, the goal is to create a low impedance path for fault currents to flow back to the source. This low impedance path minimizes the voltage rise on equipment enclosures and structures during a fault, thereby reducing the risk of electric shock. The earthing system should also be designed to limit the ground potential rise, which is the voltage difference between the earth near the substation and remote earth. Excessive ground potential rise can create hazards for people and equipment outside the substation fence. To achieve effective earthing, the earthing mesh is typically buried in the ground around the substation. The mesh is made of conductive material such as copper or aluminum and is designed to provide a large surface area for current dissipation. The mesh is connected to the steel reinforcements of the building and other structures to ensure that all conductive parts are bonded together. The size and spacing of the mesh conductors are determined based on the expected fault currents and the soil resistivity. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable because it allows fault currents to dissipate more easily. In areas with high soil resistivity, it may be necessary to use ground enhancement techniques such as adding conductive materials to the soil to improve the performance of the earthing system. In addition to the earthing mesh, ground rods are often used to supplement the earthing system. Ground rods are metal rods that are driven into the ground to provide a direct connection to earth. They are typically used in conjunction with the earthing mesh to reduce the overall impedance of the earthing system. The number and spacing of ground rods are determined based on the soil resistivity and the desired performance of the earthing system. When connecting the earthing mesh to the steel reinforcements, it is important to use appropriate connection methods. Thermowelding is generally the preferred method because it creates a permanent and low resistance connection. However, bimetallic connectors can also be used, provided that they are properly selected and installed. When using bimetallic connectors, it is important to ensure that the metals are compatible to prevent corrosion. Copper and galvanized steel are often used together in earthing systems, but it is important to use a bimetallic connector that is specifically designed for this application. The connector should be made of materials that are resistant to corrosion and that can withstand the mechanical stresses of the connection. The installation of the earthing system should be carefully planned and executed. The earthing mesh should be buried at the correct depth and spacing, and the connections to the steel reinforcement should be made properly. It is important to follow the manufacturer's instructions for all components of the earthing system. The earthing system should be inspected and tested regularly to ensure that it is functioning properly. The resistance of the earthing system should be measured to verify that it is within acceptable limits. The connections should be inspected for corrosion and damage. Any problems that are found should be corrected promptly. Effective earthing is an essential part of any electrical system. By following proper earthing practices, it is possible to protect people and equipment from electrical hazards. Design and installation of an earthing system should be performed by qualified professionals who have experience in this field. In addition to the technical aspects of earthing, it is also important to consider the regulatory requirements. Many countries have regulations that specify the minimum requirements for earthing systems. These regulations are designed to ensure that electrical systems are safe and reliable. It is important to be familiar with the applicable regulations in your area and to ensure that the earthing system complies with these requirements. The design of an earthing system involves several key considerations. Firstly, determining the maximum fault current. This is the highest current that is expected to flow through the earthing system during a fault. The maximum fault current is determined by the characteristics of the electrical system, such as the voltage, impedance, and protection devices. Secondly, calculating the soil resistivity. This is a measure of how well the soil conducts electricity. Soil resistivity varies depending on the type of soil, moisture content, and temperature. Soil resistivity measurements are typically taken using a 4-point method, which involves injecting current into the ground through 2 electrodes and measuring the voltage between 2 other electrodes. Thirdly, determining the required earthing resistance. This is the maximum resistance that is allowed for the earthing system. The required earthing resistance is determined by the maximum fault current and the allowable touch voltage. Touch voltage is the voltage that a person could be exposed to if they touch a grounded object during a fault. Fourthly, selecting the appropriate earthing conductors. The earthing conductors must be sized to carry the maximum fault current without overheating. The size of the earthing conductors is determined by the current carrying capacity of a conductor material. Fifthly, selecting the appropriate connection methods. The connection methods must be reliable and able to withstand the mechanical stresses of the connection. Thermowelding is generally the preferred method, but bimetallic connectors can also be used. Sixthly, installing the earthing system. The earthing system must be installed properly to ensure that it functions correctly. The earthing mesh must be buried at the correct depth and spacing, and the connections to the steel reinforcements must be made properly. Seventhly, testing the earthing system. The earthing system must be tested to verify that it meets the required specifications. The resistance of the earthing system should be measured to verify that it is within acceptable limits. The connection should be inspected for corrosion and damage. There are several different types of earthing systems that can be used in substations. Firstly, the solid earthing system. In this type of system, the neutral point of the transformer is directly connected to earth. Solid earthing systems are typically used in low-voltage systems. Secondly, the resistance earthing system. In this type of system, a resistor is connected between the neutral point of the transformer and earth. Resistance earthing systems are typically used in medium-voltage systems. Thirdly, the reactance earthing system. In this type of system, a reactor is connected between the neutral point of the transformer and earth. Reactance earthing systems are typically used in high-voltage systems. The choice of earthing system depends on the specific application and the requirements of the electrical system. Each type of earthing system has its own advantages and disadvantages. Solid earthing systems are simple and inexpensive, but they can result in high fault currents. Resistance earthing systems limit the fault current, but they can result in higher touch voltages. Reactance earthing systems limit the fault current and the touch voltage, but they are more complex and expensive. In addition to the main earthing system, there may also be separate earthing systems for sensitive electronic equipment. These separate earthing systems are designed to minimize the effects of electrical noise and interference. Sensitive electronic equipment is often grounded to a separate ground rod or earthing mesh that is isolated from the main earthing system. This helps to prevent noise and interference from the main earthing system from affecting the sensitive equipment. The design and installation of earthing systems is a complex and critical task. It is important to use qualified professionals who have experience in this field. Proper earthing practices are essential for protecting people and equipment from electrical hazards. The ongoing maintenance and inspection of the earthing system is just as important as the initial installation. Regular inspections can identify potential problems before they become serious, ensuring the continued effectiveness of the earthing system. Visual inspections should check for any signs of corrosion, damage, or loose connections on the earthing conductors, connections, and ground rods. These inspections should be conducted at least annually or more frequently in harsh environments. In addition to visual inspections, periodic testing should be performed to measure the earthing resistance and verify its compliance with the required limits. This testing can be performed using a ground resistance meter, which injects a test current into the ground and measures the resulting voltage drop. The measured resistance should be compared to the original design specifications to ensure that the earthing system is still functioning properly. Any deviations from the required resistance should be investigated and corrected promptly. If corrosion is found on any of the earthing conductors or connections, it should be cleaned and treated with a corrosion inhibitor. Severely corroded components should be replaced to maintain the integrity of the earthing system. Loose connections should be tightened to ensure a low resistance path for fault currents. Damaged ground rods should be repaired or replaced to maintain their effectiveness. The maintenance and inspection records for the earthing system should be carefully maintained. These records should include the date of each inspection, the results of the testing, and any corrective actions that were taken. These records can be used to track the performance of the earthing system over time and to identify any trends or patterns that may indicate potential problems. Regular maintenance and inspection of the earthing system is essential for ensuring its continued effectiveness and for protecting people and equipment from electrical hazards. By following a comprehensive maintenance program, it is possible to identify and correct potential problems before they become serious, ensuring the long-term reliability and safety of the electrical system.